We've worked with systems of equations before in the XY coordinate plane, but what about a three-dimensional coordinate plane? What about adding a third variable, z? That's what we're going to talk about today. Visualizing what those solutions look like can be a little bit trickier because it's three-dimensional. Each XYZ equation represents a plane, and exactly one solution is when all three planes intersect at only one point. They have one point in common. Infinitely many solutions, if they have this picture right here, if they have an entire line that is in common with all of them, a line has infinitely many points. So if they have a common line, then they have infinitely many solutions. And no solution would be where some of them cross but not all three, such as these. For solving a three-variable system, we're going to rewrite the system as two variable equations, and we're going to label them as 4 and 5, and use those to substitute, eliminate, solve for one of the variables, plug in, and then plug in again. Go ahead and pause the video so that you can write these down in your notes. All right, my first step is to choose two of these equations and use substitution or elimination to get rid of one of the variables. I see 4, 2, and x. I could multiply equation 2 by -2 to eliminate with the 4. But oftentimes it's easiest to look for whatever has a coefficient of 1 or -1, because then your numbers don't grow to be too massive. All right, so I see there's a -1 as the coefficient of this y, so I'm going to plan on eliminating y's. I have a negative here, and then I have a positive y here, so I think I will multiply equation 3 by the number 2. I still have equation 1, and then I need to multiply 2 by equation 3. So 12x minus 2y plus 8z equals -6. Now I believe we can simply add these two equations and get another equation that only has two variables. 16x, that is 0, 11z equals 6. This is equation 4. Keep that in mind. I just used equations 1 and 3 to eliminate the y's. Now I must use two other equations, so not equation 1 and 3. It could be 1 and 2 or 2 and 3, in order to again eliminate the y. It needs to be the y because I want my fifth equation to only have the variables x and z, just like equation 4. I'm going to use equation 3 again because it has a coefficient of 1 or -1, which makes my life just slightly easier. In order to eliminate these y's, I would need to distribute a -3 into this third equation. If I distribute a -3, I can easily add. Here is my copy of equation 2, and now to distribute -3 into equation 3, I will get, and now I will add vertically. 2x minus 18x, -3y plus 3y is 0. 5z minus 12z is -7z. -7 plus 9 is 2. Ding, ding, ding. We have equation 5. Again, equations 4 and 5 must have the same two variables so that we can use these two equations to eliminate another variable and then get one of our answers. Okay, so we're going to use equations 4 and 5. Can you use substitution or elimination? It looks to me like elimination, we can just straight up add these together. Look, we have a positive 16x and a negative 16x, and if I just add those, I will eliminate the x variable. So let's do that. All right, equation 4 and 5 have been written. Now we're going to add, and 16 plus -16 is 0. 4z equals 8. Z equals 2. Okay, let's see what step we're at. We used equations 4 and 5 to solve for one variable. We have one variable. Now we need to plug in that value into equations 4 or 5. So not quite the original equations, but into either equation 4 or 5 is how we're going to plug in z equals 2 in order to solve for x. I'm going to use equation 4 because it has less negatives, but it doesn't matter. Plugging in z equals 2 into equation 4 gives me 16x plus 11 times 2 equals 6. Let's solve for x. And our final answer for x is -1. Now that we have the answers for 2 of the variables, we can plug into any of the original 3 equations in order to solve for that final variable. And it doesn't matter which equation that you choose. I'm going to choose the top one. X is -1 plus 2 times y plus 3 times z is 2 equals 12. Solve for y. All right, and we have gotten the answer of y equals 5. So we have the answers to all 3 variables. We have 3 answers. We need to write our answer as an ordered triple in the form x, y, z. X was -1, y was 5, and z was 2. Now, how would you know if this is truly your solution? Well, you could plug it in. -1 for x, 5 for y, and 2 for z. And it has to be true for all 3 in order for it to be the ordered triple solution for this example. Let's try another example. My first step is to eliminate one of the variables. I see that I have a +1z in the first equation, a -1z in the second, and a +1z in the third. Oh, this looks like we don't even have to multiply. So the first step I'm going to do is add equation 1 and equation 2. When we add these equations, we eliminate our z variable. And here we've created equation 4. Now I'm going to add equation 2 to equation 3. It just can't be the same 2 that you first did. I mean, you would just be doing them over again, so that's not helpful. So I'm going to use equation 2 and 3 and add those. And my result is equation 5, 6x minus 6y equals -18. Our next step is to use equations 4 and 5 to eliminate another variable. I am going to multiply equation 4 by a -3, and that should help me to eliminate with equation 5. So equation 5 is 6x minus 6y equals -18, and equation 4 times -3 is -6x positive 6y equals +18. What's going to happen here? We're going to add and get 0 plus 0 equals 0. Because we obtained the identity 0 equals 0, which is a true statement, the system has infinitely many solutions. So we have infinitely many solutions, but that doesn't mean that just any ordered triple is actually a solution. So in order to be a little bit more specific, rather than just saying infinitely many solutions, what kind of form will the solutions take? How do we do this? We're going to take equation 4 or 5, and we're going to solve it for y. That means our ordered triple is going to have a variable in it. So I'm taking equation 5 and I'm solving it for y. Subtract 6x on both sides. And when I divide everything by -6, looks pretty nice, x plus 3. So, no matter what x may be, y will always be that number plus 3. But what would z be? Okay, so I'm going to take one of the original equations. I'm going to use substitution to replace the y with this group of x plus 3, which is equivalent to y. And as we solve this, we do end up with z is equal to 0. So there are infinitely many solutions, but all solutions will come in this form. An amphitheater charges $75 for each seat in Section A, $55 for Section B, and $30 for each lawn seat. There are 3 times as many seats in Section B as in Section A. So Section B, the seats in Section B, are 3 times the amount of seats as are in Section A. The revenue from selling all 23,000 seats is $870,000. So we're going to need an equation that covers all the number of seats and then an equation that covers the cost of the seats. So here it goes. The number of seats would be number of seats in Section A plus seats in Section B plus lawn seats is equal to the total number of seats, 23,000. Now the next equation will involve the money. So now we're talking how much cost per seat. So $75 for every seat in the Section A, $55 for every seat in Section B, and $30 for every lawn seat. And that total should be that should equal the total revenue, the total amount of money received. Now we have 3 equations and 3 variables included. So it's time to pause the video and solve this problem on your own. And your solution is 1,500, 4,500, 17,000 as an ordered triple. That means they sold 1,500 seats in Section A, 4,500 seats in Section B, and 17,000